Okay, now let's do example 2. The heights of women in the United States are approximately normally distributed with a mean of 64.8 inches. The heights of 11 players on a recent roster of the WNBA team are these in inches. Is there sufficient evidence to say that this sample is so much taller than the population that this difference cannot reasonably be attributed to chance alone? Well, now let's do some hypothesis testing. So here, our null hypothesis is that our sample is just like regular women, right? So the mean is 64.8. The alternative, and I'm just going to use a two-tailed alternative here, is that they are not like this population. We can probably guess by using common sense that they're on average taller, but we'll do a two-tailed test. It's actually more conservative. It's safer to go with a two-tailed test. So here, we'll make alpha equal to 0.05, and it'll be two-tailed. And let's draw the S-DOM here. So here, we might draw these boundaries. And because it's two-tailed, this is 0.025, 0.025, and here it's 0.95, right? So altogether it adds up to 0.1. All right, so now that we have this, can we figure out the t? Well, in order to figure out the t, we need to have the degrees of freedom. If you go to the download and go to example 2, I've listed this data here for you, and we could actually find the degrees of freedom here. So here I'll put step 3 so that we know where we are. In step 3, we need degrees of freedom, and that would be count of all of these guys, or gals, minus 1. And so we have 11 players, 10 degrees of freedom. And let's find the critical t. The critical t would be t inverse, right? Because we know the probability, the two-tailed probability, 0.05, and the degrees of freedom. And that gives us the positive critical t. So that's positive 2.23 and negative 2.23. Those are our critical boundaries. Anything outside of that, we reject the null. Let's go to step 4. So in step 4, we could start dealing with the sample. So let's figure out the sample t. In order to do that, we need the x bar minus the mu divided by standard error. Right? And so we need to know the sample's average, so x bar. We also need to know mu. We also need to know standard error, right? And standard error is going to be s divided by the square root of n. I like to write all these things down because it helps me figure out what we need. It's like a shopping list, you know? So here, I definitely know I need s. So now that I have written all these things down, I could just calculate them. So I need the average. I also need the mu, which I already know from the problem, 64.8. To get my Excel back. All right. 64.8. And I need to get my standard error, but before I do that, I need to get S, standard deviation. And then once I have standard deviation, I could take that and divide it by the square root of n, which is 11. So that's my standard error. And once I have all of these ingredients, now I could assemble my t, which is x bar minus mu divided by standard error. And I get 7.97. So that's way higher than 2.2. So I'm pretty sure I can, step 5, reject the null, right? And so if I go back to my problem, then let me see. Is there sufficient evidence to say that this sample is so much taller than the population that this difference cannot be reasonably attributed to chance alone? I should say yes, because when you're way out here, your probability that you belong to this chance distribution is so small that that it's reasonable for us to say it probably came from a different population, that the sample came from a different population. Okay, final example. Select the best way to complete the sentence. A p-value measures, so this is sort of a conceptual question, the probability that the null hypothesis is true. Well, sort of. Remember, that is the false alarm rate, right? It is when the null hypothesis is true. But it's also when it's not just that, right? It's not just the possibility that the null hypothesis is true. It's that given that you are you have a particular sample, right? So it seems to leave out some information. It's not quite complete. But I'm going to leave it alone because it's not entirely false. It's just that it doesn't have the whole truth, right? It doesn't have the condition, hey, given that you have this particular sample value. Okay, what about this? The probability that the null hypothesis is false. Well, that's not true. Even if you just remember this column was null is true, right? And so alpha is the set one, but P also belongs in there. So, this one's just not true. The probability that an alternative hypothesis is true. Actually, we haven't talked about that at all. We've only talked about having a very, very low possibility that the null hypothesis is true. But we haven't talked about increasing the probability that the alternative hypothesis is true. Besides, why would you reject the null when you have a really, really small p-value, a really, really small possibility that the alternative hypothesis is true? That doesn't make sense, right? So I'm going to cross that out. What about the probability of seeing a sample T as extreme as the one observed, given that the null hypothesis is true? Now this has our entire story, so I could cross this one out. So it's not just that the null hypothesis is true, but it's also that when you have a certain sample, you have this sample, so that's that also has to be part of the definition of p-value. So the idea is, if we have this t-value, and it's pretty dang extreme, and the null hypothesis is true, that's given, right? Let me explain it the other way. So given that the null hypothesis is true, what is the possibility of seeing such an extreme t-value? It's very, very, very small, right? And so we're trying to lower our false alarm rate. All right. So that's the end of one sample hypothesis testing.